In this video, I'm gonna go over hovering helicopter and hovering rockets. Let's start here again by a reminder of momentum and Newton's second law of motion. You remember I told you the external force acting on the system will be delta P over delta T, rate of change of momentum. And then let's substitute the momentum for mv, expand the delta, m delta v over delta t plus v delta m over delta t. Let's consider this equation term by term. In previous video, I explained the case of rocket in space. The rocket in space which is not acted by any external force. So external force in this case is zero. The rocket is pushing a huge amount of gas at a rate of delta m over delta t. Let's say delta m over delta t is 50. So it's 50 kilogram per second. It's just a number. And then the gas is repelled out at a speed of v. So v delta m over delta t is the force created due to this gas flow. Let's say this force is 100 Newton. The reaction of this 100 Newton will push the rocket rightward. This is 100 again. This is the reaction. And this 100 will create acceleration because it's going to be m delta v over delta t. Delta v over delta t is acceleration of the rocket. So in the case of the rocket in space, why the rocket accelerates? Because there is no external force and action-reaction accelerates the rocket. Of course, we have the same acceleration for the gas leftward, but we always consider the acceleration of rocket. Now let's make an external force to impede acceleration. What do I mean by that? Let's say there is a big wall, a very strong, huge wall, which can easily prevent any motion. So if the rocket is exerting 100 Newton to the wall will react 100 Newton, and we cancel that force. So the rocket won't have any acceleration. Here the acceleration is zero. Now consider the rocket. Just consider the rocket. Here the rocket is acted by a reaction force due to the gas flow, 100, and an external force of 100 due to the wall, and they cancel each other. Now let's consider this case. This is a rocket which is trying to lift up, but it can't. The engine is not strong enough to accelerate the rocket. What's the reason? The rocket is hovering but not accelerating. Actually, there is a v delta m over delta t 100. Now let's say due to gravity, the rocket is lifting up on the ground, from the ground. And so it's an 100 Newton of force due to the weight. So this 100 and this 100 cancel each other because there is a reaction on the rocket, 100 due to that action reaction between the rocket and the gas, and this 100 is canceled by this 100. So the rocket is hovering now. It's not accelerating. Helicopter is exactly like that. Let's say the helicopter with a rotating blade is pushing a mass, a constant rate of mass like delta m over delta t at a speed of v. Okay, this is the helicopter. So this v delta m over delta t is creating a force. Again, let's say this force is 100 downward. The reaction on the helicopter is 100 upward. And if now the mg, the total weight of the helicopter, is again 100, the helicopter is hovering, it's not accelerating. This is today's lesson. So let's consider that again. Hovering helicopter. Here I have a helicopter. The total weight of the helicopter is mg downward, and a mass of delta m at a rate of delta m over delta t is pushed down in every second at a speed of v due to rotation of the blade. So it will make a reaction. I told you what this reaction means. And then here we have F equals m delta v over delta t plus v delta m over delta t. Now be very careful. Here the acceleration is zero because we have already supposed that helicopter is hovering. Delta v over delta t is zero. There is no acceleration. And the external force acting on the helicopter is mg. Now v delta m over delta t is exactly equal to F2. Of course, F2 is the reaction of that, but they are equal, but opposite. That's all. So here we have mg equal to v delta m over delta t. This is the condition for hovering helicopter. Can we use it for the hovering rocket? Of course you can. It's the same thing. For the hovering rocket, we have the same thing. Let's say the rocket is hovering. It tries to lift up, but it's suspended in the air. So downward force of mg, let's say mg, is cancelled by the reaction force of v delta m over delta t. That's all. The rocket is hovering. It can't accelerate, it won't ascend and won't descend. It will suspend in the air. Now let's have some problem solutions. A helicopter of mass 1500 kg is hovering in the air. The mass of the air pushed downward in every second is 300 kg. So the mass of the helicopter is 1500. Let's say g is 10. And delta m over delta t seems to be 300. Why? Because in every second. So it's the delta m over delta t 300. Okay, now we can easily solve this problem. Let's say mg is 1500 times, let's take the g to be 10. So it's mg here. So it's 15,000. And v delta m over delta t. Here the delta m over delta t is given to be 300. And so the speed of the air flowing downward, the v, is going to be 15,000 divided by 300. The answer is 50 meters per second. This is the speed that the air is pushed down. We should keep this speed flow to hold the helicopter at this specific constant height. Otherwise, it will drop or may ascend. If we increase the v, it will ascend. If we decrease the v, it will descend. You may have a question why helicopter can, if let's say we increase the v to 60 meters per second, what happens? Okay, a helicopter will accelerate upward. And the question is that, okay, if we keep this rate 60 meters per second, why the helicopter is not accelerating forever? It's impossible because the density of the air will not be the same in very high altitude. And so delta m over delta t will change. This is why the helicopter cannot go to infinity anyway, due to the low density of the air in high altitude. A toy helicopter of mass 0.8 kilogram hovers motionless above the ground. The rotating blades of the helicopter force the initially stationary air to move downward at a speed of 9 meters per second. So the v is 9 meters per second downward. Calculate the mass of the air pushed downward in 1 second so that the helicopter can remain stationary. Okay, let's do the same thing. mg downward, and here we have v delta m over delta t upward. We put them equal, and you know that the goal of the question is not delta m, but it's the mass of the air in 1 second. So I need delta m over delta t in this question. Let's plug in the values. 0.8 is the mass of the helicopter I used here. This is g. Let's take the g 9.8. 9 is the speed, as I mentioned, and then delta m over delta t can be 0.87 kilogram per second. Look at the next part of the question. The density of the air is this, 1.2 kilogram per cubic meter. The helicopter has a single rotor. What does it mean? Some helicopters have two rotors. They have this shape like, two rotors. One here, one here. So it's a little bit different. So forget about it. It just has a single rotor with a few blades. Estimate part I, surface area spanned by the blades of the rotor, and double I, the radius of the blade. Let me tell you something. You know that when the blades are rotating, actually they are spanning a circular area in the air. Okay, let's say this is the circle. Okay, that's the area of A. First, we are looking for that A, and then we can find the radius accordingly. Radius of this area, circular area. Have a 3D imagination. Here the helicopter is pushing the air downward using its blades. So it will make almost a cylindrical shape in the air. This cylindrical shape has an area of air at the top. You are looking for that. And let's say at the time of delta t, it will push the air for a distance of h. So h is the distance traveled by the air at the time of delta t. Okay? H could be v delta t. Agree? V delta t. Because the air is supposed to have a constant speed of 9 meters per second. So it's v delta t. Now the volume of the cylinder is area of the base times h. So it can be A times V delta T. Well, and then go back to the basic definition of density. Density is mass divided by volume. Okay? Let's say the mass to be delta M. So delta M is going to be rho times volume. And it's going to be rho times volume is here. A V delta T. We can use it easily in this equation. Look, here I have delta M over delta T, which has already was found in the previous part, 0.87. And then here I substitute delta M for rho times volume, rho times H, again, rho A V delta T. That's all, rho AH, sorry. Rho AH, so rho A V delta T. H is V delta T here. Okay, almost we are done. Let's put the values. Of course, delta T is cancelled by this delta T in downstairs. Rho AV, this is the V. We know that it's 9 meters per second. And density of the air given here, 1.2. And right side, we have already found it. So the area is going to be 8.1 10 to negative 2 meters squared. Then we can use the formula of the area of the circle, pi r squared, and then we can easily find the radius. I've already converted the radius to centimeters, so it's 16 centimeter. The area of the circular area spanned by the blades. Thank you for watching this video. Please take notes and review the lesson. See you.